Welcome to our deep dive into the world of Albert Einstein. Specifically, we'll be looking at his theory of relativity. Our source for this deep dive are some excerpts from a Spanish-language biography of Einstein. Now, I know what you might be thinking, physics equations may be a little dry, but trust me, this isn't just about the science. Einstein's ideas completely changed how we understand basic concepts, things like time, space, and even gravity. And you know what? It all started with pretty ordinary things. Things like a compass, trains, even an elevator.
Yeah, it's amazing how those everyday objects became these stepping stones, to some of the most revolutionary ideas in physics. Einstein just had this way of connecting the dots in ways that nobody else really had even thought of.
Yeah, definitely. So let's start at the beginning with his early life. The biography tells us that even as a kid, Einstein wasn't just intrigued by,
Yeah.
A compass pointing north. Like most kids are fascinated by that. But he was obsessed with the, unseen forces making it happen.
Yeah, you can almost see the gears turning in his young mind,
Yeah.
already trying to unravel these mysteries of the universe.
Totally.
And that was just further fueled by his family's involvement, in the world of electromagnetism. Their factory produced electrical equipment. Imagine growing up surrounded by cutting-edge technology. I mean, this constant exposure to technology, especially devices like trains and clocks. It really became crucial in how he explained his theories to the world later on.
Yeah. And it wasn't just the technology itself. The biography describes Einstein as a bit of a rebel, constantly questioning teachers and challenging the school system. He wasn't satisfied with, just rote memorization. He craved something deeper.
Yeah, he was very fortunate to have found a mentor in a guy named Max Talmy. He was a medical student who really recognized Einstein's thirst for knowledge. And Talmy provided him with books on science philosophy, just nurtured his curiosity and expanded his horizons beyond kind of the confines of traditional education.
That's so important.
Yeah.
I think it's a powerful reminder that learning should be about exploration, not just, memorization.
Yeah.
So we've got young Einstein, curious mind immersed in cutting-edge technology. And he's got this mentor who really understands his potential. But to fully appreciate the impact of his work, we need to take a step back and look at the state of science in the late 19th century.
Okay, so at that time, the dominant force in physics was Newtonian mechanics. And it worked really well. It explained a vast range of phenomena, from the motion of planets to, even just a simple pendulum. But it started to show some cracks when scientists began exploring electromagnetism.
Right, and scientists like Coulomb, Oersted, Ampere, and Faraday, they were all making groundbreaking discoveries about electricity and magnetism. And they started to realize that these weren't separate forces, but actually interconnected aspects of the same phenomenon.
Think about that. Electricity can generate magnetism, and magnetism can create electricity. This relationship was completely unexpected, and it really challenged the foundation of Newtonian physics.
And then comes James Clerk Maxwell. I mean, what a genius. He took all these discoveries and developed a set of equations that unified electricity, magnetism, and light.
Light, can you believe that? These seemingly disparate phenomena, all woven together in Maxwell's framework.
Absolutely incredible.
But his equations also introduced this really perplexing concept of the ether. So the prevailing thought at the time was that waves, like light waves, needed a medium to travel through, just like sound waves need air, right? So they believed light waves needed this invisible, all-pervading substance. They called it the ether.
And this is where it gets really interesting. Scientists devised all these experiments to try and detect this elusive ether, the most famous one being the Michelson-Morley experiment. They expected to find, definitive proof. But guess what? Nothing. The ether just refused to show up.
Yeah, it was like one of the most meticulous experiments in history, designed to confirm this widely held belief. And it failed spectacularly. It was like nature was sending us a message, like, you're missing something fundamental here. And this is where Einstein enters the picture.
Okay, so the year is 1905. Einstein is working as a patent clerk, not as a university professor or anything like that. And he publishes not one, not two, but 4 groundbreaking papers. It was his Annus Mirabilis, or his miracle year.
It's mind-blowing. Someone outside of academia, reviewing patents, revolutionizes our understanding of the universe, speaks to the power of independent thinking.
For sure. So these papers covered topics like Brownian motion, which provided evidence for the existence of atoms, and the photoelectric effect, which showed that light can behave as both a wave and a particle. This one actually won him the Nobel Prize.
Yeah, but for this deep dive, we're going to focus on the paper that introduced his theory of special relativity, where he lays out these 2 simple yet profound postulates that changed our conception of space and time.
Okay, so the first postulate states that the laws of physics are the same for all observers. in uniform motion. So whether you're standing still walking or riding a train, the laws of physics apply equally to you. Seems pretty straightforward.
Yeah, but the second postulate is where things get a little mind-bending. It states that the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. So even if you could chase a beam of light at incredible speed, you would still measure its speed to be the same as someone standing still.
Okay, two simple postulates, but with some wild consequences. We'll get into those after this.
Yeah, those postulates may seem simple at first glance, but they lead to some pretty remarkable and counterintuitive consequences like time dilation.
Time dilation. Okay, now you got my attention.
So imagine you have two identical clocks, right? One stays here on Earth, and the other is sent on this high-speed journey through space. Now, according to Einstein's theory, the clock that's traveling at high speed will actually tick slower than the clock that remained on Earth.
Hold on. So you're saying that time itself slows down for the clock that's moving faster?
Yeah.
That's incredible.
Yeah, okay. It is. It means that time is not absolute, as we intuitively think it is. But it's actually relative to the observer's frame of reference. The faster you move through space, the slower time passes for you, relative to someone who is stationary.
So theoretically, if I were to travel at the speed of light, time would essentially stop for me.
Theoretically, yes. But of course, reaching the speed of light is impossible for anything with mass.
Okay, well, that's mind-blowing enough for me. So you mentioned another consequence of Einstein's postulates, length contraction. Can you explain that a bit more?
Okay, so picture this. You're observing a spaceship traveling at near the speed of light. As it zooms past you, it would actually appear shorter in the direction of its motion.
Wait, so it's not an optical illusion or something? The spaceship actually shrinks?
Exactly. From your perspective as a stationary observer, the spaceship's length is actually contracted. And again, this all comes down to the relative motion between you and the spaceship.
This is so strange and fascinating. Now, what about this relativity of simultaneity? You mentioned that earlier, and it sounded especially intriguing.
This one is perhaps the most counterintuitive of them all. It really challenges our fundamental understanding of now. Imagine two events happening in different locations. Let's say a firecracker explodes in New York, and another one explodes in London at the exact same time, according to clocks in each city.
So the events are simultaneous?
Well, not necessarily. If you were on a spaceship, traveling at a significant fraction of the speed of light, you might actually observe the firecracker in New York exploding before the one in London, or vice versa.
So what is considered simultaneous depends on the observer's motion.
Exactly. Simultaneity is not absolute, but relative to the observer's frame of reference.
Wow. Einstein's theory really turns our everyday understanding of space and time completely upside down.
It does, and this is just the tip of the iceberg. We haven't even touched on general relativity, which brings gravity into the picture.
That's right. So how did Einstein go from these mind-bending concepts of special relativity to tackling gravity, the force that keeps us all grounded,
Well, special relativity was groundbreaking, but it had a major limitation. It didn't account for gravity, Newton's law of universal gravitation, which had been the standard for centuries, assumed that gravity acted instantaneously across vast distances.
That doesn't really sound right, considering that nothing, not even light, can travel faster than the speed of light.
Exactly, and that was a huge problem for physicists at the time. How could gravity be reconciled with the cosmic speed limit imposed by special relativity? It was a puzzle that Einstein wrestled with for years.
And then he had what he called his happiest thought, right? This breakthrough that led him to general relativity.
That happiest thought was the equivalence principle, the idea that gravity and acceleration are fundamentally indistinguishable. Imagine you're in an elevator and it suddenly starts moving upward. You feel heavier, right? As if gravity has increased. But that feeling is identical to what you'd experience if the elevator was stationary and a powerful force was pulling you upward.
So you're saying there's no way to tell the difference between being in a gravitational field and being accelerated.
Precisely. And this realization led Einstein to a truly revolutionary concept. Gravity is not a force in the traditional sense, but rather a curvature of space-time caused by mass and energy.
Okay, now you're really blowing my mind. We need to unpack this. What exactly do you mean by space-time?
Imagine a trampoline.
Yeah.
If you place a bowling ball in the center, it'll create a dip in the fabric, right? Now, if you roll a marble across the trampoline, it won't travel in a straight line anymore. It'll curve around that bowling ball.
Okay, I think I get it.
Right.
So massive objects like stars and planets create these dips in space-time. And that causes other objects to move along these curved paths,
Okay.
which we perceive as gravity.
Exactly. It's not that the Earth is pulling you down with some mysterious force. It's that you're following the curvature of space-time, created by the Earth's mass.
So gravity isn't a force pulling us down, but the shape of the universe itself guiding our motion.
You got it. Einstein's theory completely reimagined our understanding of gravity. And guess what? This new way of thinking about gravity led to some pretty wild predictions that were later confirmed by observations.
Okay, predictions. So what kind of predictions did this new understanding of gravity lead to?
Well, one of the most stunning predictions was that light itself could be affected by gravity.
Wait, light doesn't have mass, right? So how could gravity influence it?
That's the thing about Einstein's theory. It's not about a force pulling on objects, but about the curvature of space-time itself. And since light travels through space-time, its path would also be affected by massive objects.
So like a beam of light passing by a star would actually bend.
Exactly. And this prediction was famously confirmed during a solar eclipse back in 1919. Scientists observed that the light from distant stars was bent as it passed by the sun, providing really compelling evidence for Einstein's theory.
Wow, that must have been a huge moment for science.
It was a monumental event, catapulted Einstein to global fame, and really solidified general relativity as this revolutionary theory. It transformed our understanding of the cosmos, showing that space and time weren't just a backdrop, but active participants in the universe.
So what other predictions came out of general relativity?
Another successful prediction was the precession of Mercury's orbit. Astronomers had long observed that Mercury's orbit wobbled slightly more than predicted by Newtonian physics.
It was a tiny discrepancy, but it couldn't be explained.
Right, and Einstein's equations perfectly accounted for this anomaly, a small but significant victory. That demonstrated the incredible accuracy and predictive power of general relativity.
And what about black holes? I feel like we can't talk about Einstein and gravity without mentioning black holes.
Of course, black holes are a truly mind-boggling consequence of general relativity. They're regions of space-time where gravity is so intense that nothing, not even light, can escape.
It sounds like science fiction.
I know, but they're very real. And we now have strong evidence for their existence throughout the universe. They're formed when massive stars collapse at the end of their lives, concentrating their mass into an incredibly small region of space.
So what happens at the center of a black hole? It sounds like the laws of physics would completely break down.
That's a question that continues to baffle physicists. We don't fully understand what happens at the singularity, the point of infinite density at the heart of a black hole. It's where our current theories kind of reach their limits.
It's fascinating. And a little terrifying to think about.
It is, but they're also incredibly important. Black holes play a major role in the evolution of galaxies and the structure of the cosmos.
Amazing. How something born out of a theory can have such profound implications for the universe.
Speaking of mind-blowing implications, general relativity also predicts gravitational lensing.
Gravitational lensing?
Yeah, so imagine a distant galaxy whose light is traveling toward us. Now, if there's a massive object, like a cluster of galaxies, located between us and that distant galaxy, its gravity will actually bend the light coming from the more distant galaxy.
So instead of seeing a single image of the distant galaxy, we might see multiple images, or even like distorted arcs and rings of light.
Exactly. It's as if the massive object is acting as a giant cosmic lens, magnifying and distorting the light from objects behind it.
That sounds incredible.
Gravitational lensing provides stunning visual evidence for the curvature of space-time. And it also allows astronomers to study distant objects that would otherwise be too faint to see, like having a natural telescope built into the fabric of the universe.
It's incredible to think about Einstein's impact on our understanding of the universe. But his work wasn't limited to just physics, was it?
No, not at all. He was also a humanitarian, a pacifist, and a global icon whose ideas and influence extended far beyond the scientific realm.
Einstein's life story is really a testament to the power of curiosity, imagination, and challenging conventional thinking.
He wasn't afraid to question the status quo and pursue ideas that seemed radical at the time.
And yet, despite all his accomplishments, he spent the later years of his life searching for something that ultimately eluded him. A unified theory that would combine gravity with electromagnetism.
Yeah, he believed there should be a single, elegant framework that could explain both the force that governs the cosmos and the force that binds atoms together, a challenge that consumed him for decades, but he was never able to achieve this grand unification.
So even Einstein, with his incredible intellect, was humbled by the mysteries of the universe.
I think it just shows that even the greatest minds have their limits. But his quest for a unified theory continues to inspire physicists today, as we search for this theory of everything that would unify all the fundamental forces of nature.
We've covered a lot of ground in this deep dive, exploring Einstein's life and the mind-bending implications of his theories. It's really incredible how these ideas born from thought experiments and equations have revolutionized our understanding of the universe.
And his legacy extends far beyond his scientific achievements. He taught us the importance of questioning, imagining, and embracing the unknown. His life and work are a constant reminder that the universe is full of wonders waiting to be discovered, and that the pursuit of knowledge is a journey without end.
Exactly. And who knows what incredible discoveries await us in the future. Perhaps inspired by Einstein's spirit of inquiry, you'll be the one to make the next groundbreaking revelation about the universe. Keep questioning, keep exploring, and never stop wondering. Thanks for joining us on this deep dive into the world of Albert Einstein